In this chapter, we're not going to cover that many different sections. In fact, this will seem like a pretty slim module and chapter compared to last week. I would like you to skim sections 20.1 and 20.2. This will be sections that cover the application or the computer applications of Gaussian elimination. How Gaussian elimination progresses is very similar to how we learned to complete Gaussian elimination with back substitution back in chapter 7, but there will be additional requirements associated with the computer applications that will address such things as pivoting and the number of mathematical operations. 20.3 will introduce an alternative to Gaussian elimination with back substitution that we would not have seen before. And in 20.4, we're going to be looking at some norms of vectors and matrices and condition numbers of matrices that are useful when describing properties of a vector or a matrix. And we're not going to cover any of 20.5 to 20.9. We'll get some characteristics of computer applications of Gaussian elimination are that error can creep into the calculations as a result of relatively small numbers occurring along the diagonal term. So one of the things that we do in order to avoid this is use pivoting or partial pivoting techniques to try and rotate or to move the various rows of the matrix around in order to make sure we have as large a number on the diagonal as possible whenever needing each row. So we manipulate the ordering of the rows in order to avoid small numbers on the diagonal. So that's the second bullet point there, is how we deal with it is with partial pivoting. One of the other characteristic features of Gauss elimination is that when you have n equations, Gaussian elimination typically has the number of operations involved being of the order of n to the third. So when we go up from, we've only dealt with 3 by 3 matrices, but when you go up to very large models, the number of mathematical operations in Gaussian elimination becomes huge when you have to cube that number of unknowns. This makes Gaussian elimination particularly lengthy and a challenging task when we move to three-dimensional modeling tasks. So those are just some features. So wouldn't it be nice if there were some possible alternatives to Gaussian elimination? Yes, it would, and we'll be introducing some of those. Sticking with the issue of error in Gaussian elimination, consider the system of equations shown here. If you recognize that all mathematical operations in a computer have limited precision, if we just arbitrarily choose 4-digit arithmetic in Gaussian elimination without pivoting with that set of equations shown there, you'd get the end result of 4 minus 1.012 and 2. But if you just complete row exchanges to get rid of that leading 0.002 on the diagonal in the original ordering of the rows, then you get the solution of 111, which is the correct solution. So one of the problems of one of the reasons why we end up with huge problems in some results is because of small numbers on that diagonal. And this provides an example of how that can present itself. So we need alternatives to Gaussian elimination for a couple reasons. Gauss-Seidel is an alternative to Gaussian elimination. It is an iterative method that, of all the things you've seen, its closest analogy is what we saw in the last chapter when I talked about fixed point iteration to try and find a root. Essentially, we're doing something like that, but for multi-dimensional cases. And while it wasn't particularly helpful Back in chapter 19, I talked about how it's not a very reliable method. Gauss-Seidel is a fairly reliable method. When it works very well, and it's fairly predictable when it works. So now we're going to spend some time on this, and it's this iterative method is very much worth considering. Gauss-Seidel is used sometimes to find a solution, and it's also used to take an approximate solution, and you might take an approximate solution and then apply a couple of rounds of Gauss-Seidel iteration, and that can help overcome problems that might have been introduced due to error or limited precision in Gaussian elimination calculations. So Gauss-Seidel has a lot of different applications. Let's consider an example so you see how it works. This is just a 3x3 example. We wouldn't need Gauss-Seidel in order to be able to find this solution, but we can. So what you do is with these three equations, you'd rewrite equation 1 so that you solve for x1 equals and rearrange the terms so you can get the equation 1 in that form. Then you rewrite equation 2 to solve for x2 equals, and you just arrange the terms corresponding to that. Then in an analogous way, you rewrite equation 3 for x3. Then you start with some initial guess, and then you iterate until you get your solution. There's actually two different kinds of methods. In Jacobi iteration, you just take an earlier estimate and then you update all the x's at the same time, and then you collectively update and say, okay, now that's my new estimate for my solution vector, and you update all of the numbers at the same time. In Gauss-Seidel, we do something that is, it starts out the same, so you use the first equation to solve for a next estimate of x1, and then when you get to the second equation, you have to have an initial estimate of all the x's. What you do is you say, hey, I just updated x1 in the last equation. I'm going to use that updated x1 instead of my x1 of the last guess. So it just, there's only a slight difference, and you may have to see this in some of the example problems to be able to see the difference. But Gauss-Seidel is usually a faster method, but it takes a little slight bit of additional effort in programming. So, but they're fairly similar, and they both work about the same. But Gauss-Seidel is typically going to converge to the solution a bit more quickly. When does these converge? You might remember back in chapter 19 that when we use fixed point iteration, we didn't always get iteration to work. And if you remember, it depended on our formulation of g having to have a derivative that was less than 1. We actually have a very similar thing here. If you rewrite the matrices, and your book goes on about this at length, but it comes down to the formulation of this matrix C that's needed in order to apply the iteration. If that has a norm that's less than 1, and I haven't introduced norm yet, that doesn't come up in the book till the next chapter, but if the norm of the matrix is less than 1, then Gauss-Seidel will converge. In practical applications, a matrix that is strictly diagonal dominant will converge, and that might seem, first of all, let me explain what diagonal dominant means. That means the term on the diagonal, if you look at its absolute value, is larger than the sum of all the other terms after you take the absolute value of each. This actually might seem like it would be rarely occurring, but in practical applications such as numerical modeling for finite element or finite difference or many different methods, diagonally dominant matrices are the most common. In fact, it's hard to get away from matrices that aren't diagonally dominant in many numerical modeling applications. So when we have a diagonally dominant matrix, you'll know that it's going to converge by the Gauss-Seidel method. In section 20.4, we cover vector norms and matrix norms, and on page 866 you'll see the definition of 3 commonly used vector norms. You're already familiar with one of these. We'll get to it. The first vector norm is called the L1 norm. And to calculate this, you simply take the absolute value of each of the terms and sum them up. That's the L1 norm. And if so, on the left, you'll see, if you see the double vertical lines on either side of the vector with the subscript 1, that's the L1 norm. The L2 norm is the one you're probably familiar with when you think about what's the length of a vector. This is how you would calculate it. You would take each of the terms, square it, take the sum of those, take the square root of that, and you have the L2 norm. Lastly, there's the L infinity norm, which is to take the absolute value of each term in the vector and then take the maximum component. So when we look at the example of the four-dimensional vector 1, 2, 1, minus 1, when we calculate the L1 norm, we would simply sum the absolute value. So we would have 1 plus 2 plus 1 plus 1, or would have L1 norm of 5. For the L2 norm, we would take each of the terms and square it. So we would have 1 plus 4 plus 1 plus 1, take their sum, take the square root of it, and we have an L2 norm of the square root of 7. Next, we have L infinity norm, where we would take the absolute value of these, take the largest, and we would have an L infinity norm of 2. So those are the different vector norms that are in common use. On matrix norms, which are defined on page 861, we have 3 in common use. The first is probably less common than the other two. The first is the Frobenius norm, where you take each of the components of the matrix and square them and then sum them all up and then take the square root of that. The next one is the column sum norm, where you take the absolute value of each of the terms and sum each column and take the maximum of those sums. And then you have the row sum norm, which is to take the absolute value of each of the terms, sum them across the rows, and then take the largest or the maximum of those row sums. So those definitions of the various matrix norms are fairly straightforward given their name. The only one that takes a bit of remembering is which one is the Frobenius norm, but the column sum norm and the row sum norm help you, just in the title, be able to know which of the components, which of the methods are involved. I wanted to spend just a moment talking about how vector norms and matrix norms are related, and we can define the relationship using the form the matrix norm would be equal to the maximum of the vector norm that you get with a times x over the vector norm x. And this definition is useful because it can show you that what we know as the L1 norm, vector norm, is what leads to the column sum matrix norm, and the L infinity vector norm is what leads to the row sum matrix norm. So they are related, and this is where those definitions of those different matrix norms come from. Lastly, we want to look at the condition number of a matrix, which is described using the kappa of A. So that's the symbol that we'll use. And you find this by taking the matrix norm of A and multiplying that by the inverse of A and find its the matrix norm of it. And you multiply those two together and you get the condition number. Condition number is very useful in applications because it can help us decide when it can help alert us when we're going to have a problem. A very low condition number is what you want. What you want to try and avoid is problems that lead to a very high matrix, a very high condition number in your matrix. So if you end up with a matrix with problems, often you try and explore what's gone wrong, why do you have error coming in, and often it's associated with a high condition number, and that might be reported in applications that you see in the future. So you rarely will be ever programming these on your own, but if you ever see that your system of equations is associated with a high condition number, this might help you understand why that came about.